I'll just sit down, right? I don't have to get up.
You can introduce yourself.
Yeah, yeah. So I'm Zé Pedro. Yeah, that's kind of that diminutive. My real name is actually just José Pedro. I'm a DevRel engineer at Aztec Labs. I joined in February, so kind of 6 months ago. I joined as a DevRel, so I was before in a similar product called Polygon Nightfall at Polygon, and so it just made sense to join Aztec for some ZK. So this is when I joined, we were still working on Aztec Connect, which was like a ZK rollup, and so yeah, this was interesting. Cool. So yeah, just a quick note. I'm gonna be mostly talking about Nior again because I know very little about ML, and this is and ZKML even less. And so this is more like presenting Nior, and then we can talk a little bit about how can Nior be made into a ZKML enable. Yeah, given how good it is in Nior and how much could it help in that. So just for our rundown, I'm gonna talk about ZK. I think everyone is gonna be, I mean, even for those who are more about ML, probably this could be interesting, but exactly what are the problems of ZK, what are we facing? I'm going to talk a little bit about Nior as the ZK language, the ZK-DSL language, and why did we do it, and where are we heading? I'm going to talk about our build plan because I'm going to do a little bit of a demo at the end. So I'm going to just run down what the demo is going to be about. Hey. And then yeah, then we can hack stuff and try to do something. So we know the ZK proofs are powerful. We can prove a bunch of things about, yeah, I mean, I think, yeah, a bunch of things from Ethereum storage proof, for example, and proving that you own an NFT without disclosing who you are or what NFT do you own. And these kind of things are very, very powerful, not only on Ethereum, but like in the real world, like you could have like a real world oracle with zero knowledge proofs about the exchange rate of the dollar, the euro, something like that. Could be, they are very, very powerful, but just with, I think it was on Star Wars, right? That this says that with great power comes univariate polynomial commitments. Mm-hmm. So that's kind of one of the problems. I think the problem of ZK is like if you're not very well versed in mathematics, you can have a very bad time just navigating the whole ZK space. And so yeah, so the thing about ZK is that you can use it in pretty much all these fields. You can use in corporates, in privacy, in compliance, in gaming, and special identity. People are talking about ZK, using ZK for identity a lot. This is really cool, really interesting, and we've been having that in Nior as well. And then we have the whole blockchain space that seems like it's gonna, yeah, it seems like it's really not a mainstream thing, right? Where we have DeFi, everyone talks about DeFi and gaming. I put crypto twice because everyone's talking about crypto so much that it deserves to be here twice. Yeah, but we all know that blockchain is just much more than this, and ZK is also much more than this. So we want Nior to be tackling these two spaces, basically the ZK space, but also the ZK and blockchain space. So as I was saying just before, the Web2 world is very interesting for us as well using Nior, and we want to tackle that too. Yeah, so ZK is really powerful for everything, and so Aztec's kind of in this intersection between blockchain and Nior, and this is one of the reasons with Nior. One of the reasons why Nior is not a language for Aztec. It's a language that you can do many things, including smart contracts in Aztec. So that's just one of the things you can use Nior for, and you can also use Nior as a smart contract language for all other chains as you wish. So we need this usable universal ZK DSL. There are many other solutions. We can talk about Circuitry, for example. But again, we want something that's gonna be easy and nice to write with. And so Rust is a nice language. Kev likes Rust, and so he decided, I'm just kidding, but we decided to literally copy Rust syntax. And that's kind of our goal. Is if you write Rust, you're going to be able to understand and read a Nior circuit very, very, very easily. They're just like one or two words that are different, and then everything is just the same. And so yeah, you can literally not tell the difference between Rust and Nior. And just gonna give you a quick example. So if you try to spot the difference between these two bits of code, yeah, it's gonna be very different. Apart from the background, that one of them is Nior and another one is Rust. They are literally the same. Unless you want to constrain something in Nior, then you're gonna use the assert keyword, and that's one that's not in Rust. And so, but once you scratch the surface, they have nothing to do with each other. So there's no concept of heap, for example, of stack or heap in Nior, because it's all polynomial. It's all polynomials. There was no concept of this kind of memory in that sense that Rust uses it. And so this is one of the challenges, is how to make a language look similar, but then once you start scratching the surface, it's a completely different one. And so most of all, we want to write code and not write circuits. Nothing against writing circuits. I love that. When I started with ZK, I started with Circuitry, I would draw the circuit and then all the lines, design all the constraints. And that's cool. That's okay. But most developers, especially the ones that are writing smart contracts nowadays, they want to write code. They don't want to write in a completely new paradigm of like programming paradigm. So, and more than that, it's that we want also for more experienced developers to be able to use these abstractions in an easy way. I mean, if you want to build something, it's very complex, but somehow in your code, you need like ECDSA signature verification. You want it to be easy to write. You don't want to write the whole ECDSA signature verification thing. You want it, okay, I just want this, it can just be one line. Why should I write 200 lines, you know? And so this is both for someone that just starting, just wants to assert that X is different from Y, but also for the more advanced user that just, yeah, wants to have some degree of control, but it's okay with just having very abstracted things in a very easy way. Yeah. And so, yeah, this slide is wrong. I said what tools, but I was just corrected. It's actually which tools, but sorry, English is not my main language. So yeah. Yeah. And so we are still in alpha. So it's, everything is unaudited. So proceed with care, obviously. Yeah, it's just, it's never too much to say this. So things that we have we have tests, so that's really cool. We have you can write some tests just to check that the syntax is correct, just to debug, to get some print commands, just to debug stuff, just to know that your control does exactly what you want it to do. I just noticed that it uses the constraint keyword, which is deprecated, but anyway, no problem. We have a language server, so it ties up with the tests I was just mentioning before, because you can have like a nice language server that will give you syntax highlighting, and it also like give you compilers before it compiles, and also some code lenses on VS Code, so you can click buttons and run this specific test or that specific test, stuff like that. So it's really cool. We've been working on this just to make it even easier to develop with Nior. We have obviously a solidity verifier. It could be a verifier in any other language or whatever. We don't care. You just care that you can verify your proof on chain in an AVM chain. So if you work with Cosmos, for example, and you want to deploy a verifier in Cosmos, please feel free to apply for a grant. We'll fund you to write the verifier contracts in other languages. It will be really cool. And then we have nice docs. Yeah, it's like, yeah, we've spent considerable amount of efforts engineering with our docs. We want them to be versioned, for example, and always to be as up to date as possible, and easy, and especially to be as easy to understand as possible. It tried to have the whole information you may need, but also try to be very, very easy to get started with, and just proceed and get better and better as you go. So another thing is like Nior is backend agnostic, and this is it's confusing for many people, especially when you think about like backend front end. You think about Web3, Web2 concepts, and this is like the backend of the proving mechanism, proving scheme. So this means that you could select a different backend to prove your language. And the way we do this, your proof, and the way we do this is through a language that we call an ACIR, an abstract circuit intermediate representation. And so it's a little bit like YOL with Solidity. You write Solidity, and then when it compile, it could compile to YOL, and then YOL will eventually get into your bytecode that's gonna go on chain. And here's a little bit kind of the same thing. You compile your Nior circuit into this ACIR representation, this abstract circuit in representation, and then your proving backend could understand that and prove whatever you want in a way that you want. And so we obviously are working with Bratenberg, which is the backend that we've been working the most since the beginning of time at Aztec. But there are others. We had a Marlin backend that I think the integration is broken right now. but we have some grantees working on a Halo 2 integration that they just finished yesterday. So it's kind of, yeah, it's really cool. And that's it. Basically, you have this ACIR plug in to another backend, and it will work as long as there's this understanding from the backend to understand this ACIR through what we call the ACDM. Yeah, Halo 2 is a backend developed by Electric Corp, I believe. I don't know. 34. Yeah, the Mac 34 is the team that built like the integration of Halo 2 into Nior. So
is that public? Because we had someone working very similar things.
Yeah, it's public. I don't have the repo, but I can try to find it and send it to you. Yeah, it's definitely public. So it's really cool. I'm very happy that they did it. This Halo 2 integration.
And the current background that you got, I'm sorry, the current prover that you guys use, is that also Aztec based, or
yeah? So
that's something you guys developed yourselves?
Yeah, we're still developing it. Bratenberg.
Yeah.
Bratenberg. It's very hard to say and write, but yeah, it's Bratenberg.
Is the proof generated in the browser?
Yeah, that's one of the things in our roadmap. So we had proofs on the browser, but then when we updated to UltraPlonk, we had some problems. We had some problems making it work again, and now you can now prove on your browser. We're just having some issues with the witnesses, but the proving you can do it with the browser using a package called BBJS, called Bratenberg.js. And basically that's how you would prove on the browser stuff. So yeah, our roadmap, it's like we are mostly working with IDE tools and have a nice package manager, because Nior is really cool that you can import different modules from different persons. So for example, you could import a very incredibly useful EC recover library from a guy called Colin Nielsen, and you could use that and just paste into your nargo.toml, and then bang, you can use that. But it would be really, really cool to have a package managed like npm, for example, where you can just do like cargo install, and then whatever GitHub or package you want to install, it would get from like a repo somewhere. So that's what we're working on. We're working on JESTS, so you can verify using JavaScript, TypeScript, which leads us to obviously the proofs on the browser, to be able to do that on the browser which is massive because you could, for example, play games on a browser and then prove that your game was played correctly, or just use signature, use proofs as login without like proving that you know your password without saying your password, for example, through proofs on a browser. So we're working on that, and then very tied with this is the recursive proof. So recursive proof is basically when you have one proof and you want to verify that proof within another proof, and so it's kind of a proofception, right? It's like you verify things, you verify proofs within proofs, and this is very interesting. So, for example, let's say you have a Merkle tree that's very hard, very huge Merkle tree, and you have to prove like 16 layers of that Merkle tree. You can just prove from 0 to 8, and then prove from 8 to 16, and then pick those two proofs and verify those two proofs in another proof. And so kind of do it to make it even easier. If you have like a turn-based game, like a card game, you make your play and you make that proof, and then your opponent verifies that proof and makes its play, and then you verify your opponent's proof and you make another play. And so you can have like a fixed constrained turn-based game through recursive proof. So this is very hard to do, but we are working on that, and we have it already. I actually just this morning I managed to run recursive proofs on my laptop. That's
not a quick use case, or the one that you put a constraint that I say something and then you need to send it and then I send it.
Yeah.
Because it will be for legal cases, and then you have to answer like each amount of time for a legal requirement for the request to give you something.
Yeah. Yeah, it could be a use case. Yeah. Yeah. This is really cool. Yeah. For example, if you're playing like battleships, for example, so these guys Mac 34, they work with battle. They made like a battleships version in Nior, and one of the problems is that every move would have to be settled on chain, and that makes the game basically unplayable. So if you have to make a move and then wait 15 seconds for it to be mined, that's not okay, right? But if you use recursive proofs, yes, because your opponent can just verify your proof and then play, and then you verify its proof and then play.
The number of proofs fixed, or can it be arbitrary?
It can be arbitrary as long. I mean, each recursive. So to verify one proof within a proof, it's kind of heavy on resources. So there's the limits of like, yeah, there's a limit of feasibility of your proofs. I believe one of the limits is the 4 gig RAM that your browser allows you to use on a WASM prover. So if you use two recursive proofs, you can make it okay. But maybe if you try to verify like 4 or 5 proofs within a proof, maybe it will hit some kind of limit. Even like the proving time would be big. But as long as you can verify 2 proofs within a proof, it's okay, because you can verify one and like proof 1 and 2, and then verify those into a proof 3, and then 3 and 4, and verify that. And you could basically verify the whole Merkle tree recursively if needed be. Just it will take a lot of time. So there's this trade-off. But recursive proofs is like, we are very, very excited about recursive proofs, especially when you combine that with the browser and the Ethereum storage proofs. So for our demo, our build plan. So I'm going to install NoirUp and Nargo. So if you're used to NoirUp, if you're used to Foundry App or Rust App, it's literally just you copy this line and you have like a very easy installer and version manager for Nargo. And Nargo is like cargo, but for Nior, so it's kind of Nargo, right? And so you run that, you get that tool NoirUp, and then you can use it to install nightlies and whatever. And so that's what we're gonna do. You can use NoirUp, and it will install the latest version of Nargo, latest stable version of Nargo, and then you can check if you get like a stable version of Nargo, it should be 0.7.1 at the time of I'm saying. And then I'm going to start a new project with the keyword Nargo new. That will get another project, and then Nargo make interesting. Well, yeah, not too much. and then you can write tests. As I said, test is really cool because you can test. You don't have to prove to test. It's much faster. So it's really to develop. It's a lifesaver. And then if I manage to, I'm gonna try to generate the solidity verifier and deploy and prove something in there so you can see how it works. It's not no big deal. It's just sometimes it doesn't work so well. And so yeah, let's hack. Here's my thing. So I just noticed that I'm gonna probably use the screen. So if you want to take a picture, please do it in the next 10 seconds.
Another question. So regarding the code gen verifier there, how does the gas usage look like for verifying the proofs?
Cool question. I think about 300K. Yeah, it's a lot. Yeah. Yeah. There's no way around. We can if you use standard Plonk, you could get less, but then you wouldn't prove so fast. So there's this trade-off between.
And there is only one variant there of the code of the verifier that gets generated.
Yeah.
Of course, you can write your own, but still.
Yeah, you can write your own. We've had this idea that maybe okay, fuck it. Let's just rewrite this in half to save some gas. But then it's okay, why? Right? It's like if you're spending 300K gas, that's already like a lot of gas. So yeah, there's trade-offs obviously, and this could be and will be improved definitely. So yeah, so I see no phones in here, so I think I can move forward. So here I'm gonna start a new project, as I said. So I already had Nior up. I can send you like the whole Nior up install thing. And so this is installing the latest Nargo. Probably I had the nightly install. So I'm gonna install the latest Nargo version. And so I can just check Nargo version and get, okay, because 0.1 was released, so 0.8. Okay, cool. That's cool. I hope nothing breaks because of this. So I'm gonna just create. So if you just click Nargo, you see all the things you can do with it. So I'm just gonna Nargo new project. I'm gonna cd into my project. I'm gonna code this, and here we are. And so basically this is like the anatomy of a. This is the basic project that it's gonna be spit out.
Share the screen?
Yeah.
You probably should.
Oh, I have to share this. Okay, just a sec. I have to stop and then again. Sorry about that. Yeah. Okay. I can use always this terminal, and it should be okay. Yeah. So this is the basic circuit that gets spit out. It just a simple assertion. So I know X. Everyone knows Y. I want to prove that X is different from Y. This is the code version of I know a number. Please try to guess my number, and prove that it's like prove, or in this case would be like the other way around. It's like prove that you don't know my number, right? It's like this would be like this. So this is you use the pub keyword to basically say this everyone knows. I'm going to assume that everyone knows this is part of the process. And so one very easy example is the one I was just mentioned, the email, the password thing. I want to prove that I know my password without disclosing my password. And so when I register, I just send you the hash of my password, and then hash everyone knows. I know my hash. So I send you the hash to the server. The server stores the hash, and then when I'm logging in, I just send a zero knowledge proof that I know the password, that the hash of my password is equal to the hash that everyone knows. And so if this is my password, this is my password hash. What I want to do here is something like hash the password, and then check if password is equal to password hash. And so basically this is what the circuit group wants. I want it to do that. So we need to pick a hash function. So some hash functions are not really easy to are not very ZK friendly, like Ketchak is not very ZK friendly. So I'm gonna use, for example, Blake 2s. So I'm gonna just say pass say hash, and I want this to be we support Poseidon, yeah. And so I need Blake 2s Blake 2s here, right? Blake 2s password, and then I want to assert that my hash is equal to my password hash. Okay, so this is our build plan. This is what I want to do. Obviously, I need to import a little something, so I'm gonna go to the Nior docs and basically try to see what exactly do I need to do. So I'm gonna again stop sharing because of the. I'm gonna share this. Oh shit! How can I do that? Okay, here. I'm gonna do that. So I'm gonna go to the Nior docs, noirlang.org. That will give me the docs. So what I want is my cryptographic primitive to have a bunch of hash methods. And so you see here, we have Poseidon here. And so Blake 2s, this is the one I want to basically copy. And so one thing I should notice is that it takes, I'm gonna just copy the whole thing. It takes an array of unsigned integers and spits out an array of unsigned integers. So, so I'm gonna go back to my example, which is here. And so just gonna paste this. So I want this, right? I want std hash Blake 2s password to be equal to the hash that everyone knows. So I need to I'm just commenting this just for reference. I need to use dependency std, right? So I'm basically importing the standard library. Like in most languages, you need to import the standard library. And so that's it. This is my goal. Now to run my test, one thing I need to know is I need to compute the password hash in advance. And so what I have some cheats here in another project in the London ZK week. I've done that. So let me see. Yeah, cheats. Okay. So I'm gonna space
about the field data type. I think it's like backend dependent. And I'm wondering if there's like a lower bound when you
I think it's backend dependent. There's no lower bound. We don't it depends on what kind of finite field you're using.
Yeah, well, there will be like a empirical lower bound, which is what the smallest backend is.
Yeah.
Or like the backend defining the smallest thing.
Yeah, I don't think we constrain that. I'm not entirely sure, but I could check. So basically, this cheats. It's something I just computed out of this script. So I can share with you the secret scripts. So this is basically this main script. It just gets the Blake 2s. So I can run this and basically get these fields. So basically what these are is the pre-image. So let's say this is my password and this is the hash of my password. So everyone knows the hash, only I know the pre-image. So I'm just gonna copy these sheets. Yeah, you couldn't believe me, right? Trust me, bro, that this hash is the is the Blake 2s of the pre-image. So yeah, I'm gonna just give it the same name, password and password hash. So my test will basically say main password hash, and that will assert that it is the same. So one thing I need to just check is that it requests for you wait. So this needs to be known at compile time. That's very common in ZK. So I need to know that it has 3 bytes, and here it is. This is it's and 32 bytes array of 8 bytes unsigned integers. So cool. I think this will pass. Let me see. It's trying to return. This is the circuit. Yeah, it will output the smart contract. I'll show you. Yeah, yeah. But yeah, write a circuit to write a smart contract in Nior, it will be as easy as saying contract, etc. Even syntax is not here yet, so yeah, it's going to be very similar to this. So you see, you could run this test. So it's currently not working. I think there's something to implement, but yeah, this is what I was saying, the code lens thing. So now I go test. Yeah, it says that all function pass, so that's cool. If I change 1 bit, it will fail, hopefully. Yeah, it says that it will fail. So one limitation that we have currently is that you can't have tests that fail. You can't have tests that are expected to fail. That's really not cool, but we're gonna work on that.
How do you assert it for failure in the language?
Sorry?
If I want the test to fail, how do you write it there so it doesn't break it?
Yeah, that's what I was saying. We don't. You can only test things that pass. Okay. We are very optimistic. But yeah, we should have like test fail, something like that, like Foundry does, right? But yeah, it's coming. We are aware of that because
our project and we have. I mean, it's a lot of things there. It's quite complex.
Yeah.
We test things fail too.
Yeah, of course. That's standard. That's expected. And so yeah, so I'm gonna prove this. So first of all, I'm gonna run Nargo check. I'll explain what is this just in a minute while it proves. So I'm gonna run Nargo proof. So Nargo check basically. Oh wait, cannot parse integers. Oh, okay. I didn't. Yeah. So when you run Nargo check, it will basically create these 2 files, prover and verifier. So as you see, the verifier only knows the password hash, and the prover, which is me, I also know the password. So obviously I need to pass these into there. I need to put I need to pass the values so I can prove them. So this is a TOML file, so I need to make some changes here so it's valid. I think this is valid. Okay, so basically, yeah, now I can prove something. It will take a while because especially this password hash. Sorry. Especially 0.8 is, oh, it was fast. Oh, it's faster than I ever thought. Maybe they fixed it. There was some problem making them very slow. Okay, cool. So we have our proof here. It's just a bunch of trash gibberish and very difficult very difficult to understand. No problem. That's kind of the point, right? And then yeah, you can prove with Nargo verify P. So basically the idea is if I give this to you and I export the verification key, you can verify. Everyone can verify this. And
when you have a circuit with public signals, does it export it on the proof like an array?
No, it's yeah. So when you export the ACIR, it will also pass the public inputs, but it's not within the proof. We did it before, like it was the proof also had public parameters that so you would have to decode them, but we moved away from that because it was very confusing, and even in your smart contract development would make things a little bit more complex.
So then right now how it works if this circuit has, let's say, 2 public signals, a modifier and something.
Mm-hmm. Yeah, you can pass them like in a smart contract or something, or outside or off chain, whatever.
Does the proof file has those signals here?
No. No.
Where do they get them from?
Yeah, you get them from like a smart contract, for example. So there's within your contract, there needs to be a way for this password hash to be known. You can pass them via off-chain methods. You can pass them in a smart contract.
Sometimes we have public signals that are generated inside the circuit. So then it means that the user needs to generate them outside the circuit and then pass them along.
Yes. Oh. Yeah. Yeah, that's it. And so basically we have here the proof. So what we're gonna do is Nargo code gen verifier. So hopefully this will be fast as well. Okay, cool, it is. So here is the verifier contract. So this is ready to deploy. I'm gonna show you how. This is a library. there's the base contract here. It's just, you see, it's a bunch of very complex arithmetic. And then in the end, you finally have like the ultra verifier contract you can import. So if we have time, we won't have time, but I would show you how could you use this in your own smart contract. And so basically so I'm gonna just keep this, just copy the whole contract. I'm creating an Anvil network here, like my own network. I'm gonna stop sharing and I'm gonna hand back to the other, where is it? Yeah, here, to the other. Okay, here, so I'm gonna go to Remix. This is kind of one of the basic IDEs, so I can show you what's going on. So I'm gonna start like a new blank project. It's a bit small. You wanna like bigger?
Are we screen sharing it?
I think yes, right? Can you check? Yeah, okay. Because I stopped it and yeah, maybe it's just, yeah. Like this, it's okay? Yeah, okay, cool. So I'm gonna create a new file. It's got like verifier dot solve. So I'm gonna just copy all of that. Is it pasted code alert? I say yeah, no problem. I know what I'm doing. And so here I'm gonna compile it. So it will say stack to deep. So you probably know what this is. You need to enable some optimization. It's very common. So when I compile, it will hopefully compile. Okay, it's compiled. And so I take my compilation contract. I'm gonna connect to my Foundry provider, like Anvil Network, like a starter. So there's a bunch of money here. That's okay. I'm gonna deploy that. And so here's my contract. So it expects, again, you can get the verification key hash. So just to check that you're actually using the verifier contract you want to use. And then it expects like this. It expects like a proof and the public inputs. Again, these public inputs, you can pass it 0, no problem. If your public inputs are known by another smart contract or something, that's okay. You just right. So how you pass them in, it's entirely up to you. How you call this verification, whatever. It's public, so everyone knows. You can assume that everyone knows. And so yeah, what is the proof? So I'm gonna just grab the proof from the other. I'm just
this example. We don't have public input.
We have a proof. We just calculated it. Yeah.
We don't have public input.
We have the password hash, right? Everyone knows the password hash. So that's what we're gonna pass here. Yeah.
I mean, you need to use that hash and paste it into the public input field.
Yeah, because the hash, everyone knows the password hash. What you don't want to reveal is your password. You're okay with revealing your password hash. You're just not okay with revealing your password. And so what you generated is a zero knowledge proof that says the hash of my password is going to be equal to the password hash that everyone knows. And that's the beauty of the thing. So I'm just going to tell Solidity I'm using a hexadecimal string, and then I'm going to pass the public inputs. So gladly, I can have already the public inputs in here, because when I verify this off chain, it just wrote the password hash here, just in a way that Solidity likes to see it. And so yeah, here's like the byte representation of my password hash. Okay, so it's going to be a little bit anticlimactic when I call this. It's going to just say true. Yeah, yeah, okay, cool. It verifies. So if I change something in my proof, like if I take 1 byte or something, it will say, yeah, out of gas, because it enters some kind of loop and doesn't even run. It could also fail if the proof is not, if I'm passing a different, so if I'm changing something, if I'm changing something in my password, if it's instead of this, it will say like proof execution reverted. So it's kind of, the proof fails. And so this is kind of, yeah, this is kind of it, right? So you could do that. You could just pick this ultra verifier and have like another contract that uses this. So one example of that could be, for example, Nior examples. The stealth drop example, which is one of the examples me and Josh created. And here we have the airdrop, which is like a private airdrop. And here is it. I just instantiated I have a new variable here, which is the auto verifier type. And in my constructor, just pass the verifier. And then whenever I need to verify that, I just go and call verify, verify.
And this contract is really, the contract is installation. It has to be the contract in Rust or to deploy in Aztec, right?
Yes, in Nior, not Rust, but in Nior. Yeah. I'm glad you're mixing with Rust. Means that it's very similar. Yeah, so this is the way you could also have different many verifiers within your contract. And so this example is kind of a end-to-end example of how you would done your development.
What's ultra verify?
This is ultra verify because it's based on ultra Plonk proving backend, so it's called ultra verify. The previous one would be turbo verifier. And yeah, hopefully we're gonna have honk verify, which is the next iteration of the proving scheme. So that's it. I don't know if you have any questions. Any more questions?
We only have 10 minutes. So
yeah, we only have 10 minutes. So
okay.
So the ACIR you mentioned is something Nior specific, or there's many projects using ACIR?
It's yeah, for now it's kind of Nior specific because we are the ones that have been developing it. But yeah, you have the Halo 2 backend that you have this translation layer between the ACIR and whatever Halo 2 understands, and this has been done this week basically by the Mac 34 guys. But you can have that in any other proving backend. You're free to use any other proving backend.
Well, I think it's quite important to have everyone's agreed and familiar with this solution now, because everyone's been there.
Yeah. I mean, we don't want to create yet another standard. Like, there's this XYCD that's about standards. Like, we don't want that, but no one can stop you from picking the ACIR and implementing ACVM for whatever backend. Yeah. This is all open source. Just feel free to do it.
So is there a standard right now for a similar?
Yeah, it's not a standard, but yeah, it will be cool to call it a standard. Yeah, but yeah, we're happy to have this decoupling between what you write and what's exactly proving what you wrote. This is important for us.
So another question is, why are you using Peterson hash in Merkle tree?
It's a good question. I don't know. I mean, it's a very efficient hash for Merkle trees. I guess that's, but I don't know if there's other that could be maybe Poseidon could be also very. Yeah, probably. I don't know why, but yeah, we are using even here, even these circuits.
We were using hash before, and the proof was getting generated in like 30 seconds.
Yeah.
Now we're seeing under 2 seconds with the Python.
Yeah.
So.
Yeah, but this uses Peterson in the backend. Yeah.
And just an extended question for this. Why are you not using a template for Merkle tree?
The what? Sorry.
Template. You can template the hash.
Template the hash.
Hasher. Just hash.
Yeah. You mean template like in Circuitry templates?
You can use a template type for template function for the Merkle tree computation.
Yeah, I guess so. Probably, yeah. So Any other questions?
Maybe for the future steps of Nior, so you alluded to having smart contract written in Nior as well. So what else is coming there? So what you guys are working on?
Yeah, and the Nior side is mostly what I was just saying, like to have like nice npm packages you can use to install and run like verifiers of chain or something. And recursiveness, that's massive. And Ethereum storage proofs, which they are very, very related. The recursive proofs, the work within recursive proofs and Ethereum storage proofs, because Ethereum storage proofs are absolutely massive because you can prove like FTX balances is higher than zero without disclosing which wallets do they control, stuff like that. You can prove that some transaction happened on Ethereum.
With some proof of solvency, like
yeah.
One of the issues that only one company saw was that it doesn't matter if you can prove that I own above zero. If my off-chain loan liabilities are 10 times more than that.
Yeah.
So, and that's no way to prove it. Like if legally I owe you $1 million and I'm paying, I don't know, 2,000 per month, but my expenses are, and my balance can 1,000 units.
Yeah. I guess proof of solvency is a huge unsolved situation. Because I mean, you could just an example, a bank could be using crypto to buy a CryptoPunk, and that's like that's an asset, but you can't really know the price of the asset until you trade it again. So how can you count that in a proof of solvency? It's complex, I guess. Yeah.
What the recursivity proof? Speaking with the CK team from Polygon, we're speaking about some optimizations for our project. So they were like suggesting like recursivity. One of the things that they mentioned is that at least with the code of identity from Circuitry, we need to define the for loop of how many proofs are going to be that equals proof, because it's a for loop. So we need to define if it's going to be 5, 10, 100.
Yeah.
And once we define it, we cannot change it. So it's a proof. How does it work with
Yeah, I mean, you can change it once you can change it after compiling. You can't change it after compiling. But there's so you need to know exactly how much constraints are you using with a certain amount of and there's just no way around it. But there's a huge benefit from just using Nior instead of using Circuitry for that, which is the trusted setup. So when you use R1, when you use Groth16, you have like a trusted setup per circuit, and that's really not cool if you change your circuits quite often. If you're like, oh, I'm proving the verification of 3 proofs, and then you want to change to 4, for example, for effectiveness or whatever, then you have to make another ceremony, and that really sucks. And so if you can only just use one, like we are usually using the Ignite ceremony that we did when we launched Aztec first time. You can that's it. You just use one.
Is that one Groth?
Sorry?
No, is that Planck?
So Planck needs a trusted setup that's universal. So you only run it once, and it's called Ignite, and we did that already.
But Planck is a little bit bigger than Groth16.
Yeah.
Not much. But...
Yeah. It's generally slower.
Yeah.
So there's this trade-off, right? There's
it's different. It was like 220 gas units with Groth16 for the simplest proof. So it's simplest proof with signals that with Planck was like 260. It's a little not much.
Yeah. There was definitely trade-offs. I mean, to just have one trust. So when I was at Polygon Nightfall, we were using Groth16, and believe me, it was a pain to have every change we made to the circuits had a new ceremony, and that was really, really hard.
Balance, yeah.
And so yeah, when I joined Aztec, it was like, oh, finally, I don't have to care about this anymore. Just I write my circuit, I prove my circuit, and that's it. No tracer setup anymore. I just use one, it's already done. People can trust it. I mean, like millions of dollars are already being used with that tracer setup. So yeah, because it's the one from Aztec, from Aztec Connect. So yeah, I just can use that. It's like if it wasn't safe, it would be already be hacked.
All right, we'll actually have to do a hard stop today
Yeah.
because we do have something in house after this. But make sure you grab your connections and